In November of 2024, a team of researchers published a paper that quietly rewrote something scientists had accepted as fact for nearly 4 decades. The data behind it wasn't new. It came from a single 6-hour flyby conducted back in January of 1986, captured by instruments built with 1970s technology, sitting untouched in archives for 38 years before anyone thought to look at it differently. Picture that data exactly as it existed for most of those 4 decades. Rows of numbers and magnetic field readings stored on tapes and later digitized into archives, referenced occasionally by researchers writing follow-up papers but never fundamentally re-examined, treated as a closed, fully understood chapter of planetary science rather than a puzzle still waiting for the right tool to unlock it. When a team finally did look again, using modern computer modeling that simply didn't exist when the data was first collected, they discovered that everything scientists thought they knew about the strangest planet in our solar system had been shaped by a stroke of extraordinarily bad timing. This is the story of what NASA's reanalysis of Voyager 2's Uranus data revealed, why it upended 40 years of textbook science, and why it reopened a question about hidden oceans that researchers thought had been settled for good. To understand why this reanalysis mattered so much, you first need to understand just how strange Uranus looked to scientists after Voyager 2's original 1986 flyby, because that strangeness became one of the defining facts about the planet for nearly 4 decades afterward. Voyager 2 remains the only spacecraft in history to have visited Uranus up close, sweeping past during the final leg of its historic tour through all 4 giant planets, a feat no other mission has ever repeated, and one unlikely to be repeated again anytime soon, given how rarely the planetary alignment that made Voyager's entire grand tour possible actually occurs. During that single, brief encounter, lasting only a matter of hours out of a spacecraft mission that had already run for nearly 9 years by that point, Voyager 2's instruments recorded something that didn't match any other planet in the solar system. Uranus's magnetic field trapped energized particles into a radiation belt so intense it was second only to Jupiter's infamously brutal radiation environment, a belt made almost entirely of extremely energetic electrons. But almost everywhere else inside that same magnetic field, space was strangely, eerily empty, nearly devoid of the other charged particles that planets normally collect from the solar wind and from moons orbiting inside their magnetic bubble. It was as if Uranus had 2 personalities stitched together, one region packed with dangerous radiation, everywhere else an almost total vacuum, and nothing about that combination matched Jupiter, Saturn, or Neptune, the 3 other giant planets. Voyager's twin spacecraft had already studied in detail by that point in the mission. For nearly 40 years, that mismatch became one of the defining facts of Uranus itself. Scientists wrote the planet into the record as a genuine oddball of the solar system, its bizarre magnetic environment treated as a fundamental, permanent feature of what Uranus simply is, rather than as a snapshot of one single, brief moment in the planet's ongoing existence, the way a single photograph of a stormy coastline might get mistaken for a permanent description of what that coastline always looks like, rather than one unusually turbulent afternoon caught by pure chance. That label came with real consequences for how researchers thought about the rest of the Uranian system, particularly its moons. 2 of Uranus's largest moons, Titania and Oberon, have icy outer layers, broadly similar in some respects to Jupiter's moon Europa, which scientists confirmed has a vast subsurface ocean by studying subtle variations in its own magnetic environment, essentially watching how the moon responded to the magnetic field of the planet it orbits, detecting a hidden electrical magnetic field passing through it. The same basic principle engineers use to find buried pipes or cables here on Earth, just applied across hundreds of millions of miles of empty, applying that same detection method to Uranus's moons, using the magnetic field Voyager 2 had recorded back in 1986. They found nothing. No induced signal, no evidence of a hidden ocean, no reason to think Titania or Oberon were anything other than solid, unremarkable ice. For most of the last 4 decades, that was treated as a settled, if disappointing, scientific conclusion, one repeated in textbooks and popular science coverage without much further scrutiny, since nobody had any reason to suspect the original measurement itself might have been taken under unusual, unrepresentative conditions. Here's where the 2024 reanalysis changes everything, and it hinges on a detail that had been sitting quietly in Voyager 2's own data the entire time, unnoticed for decades. When the research team, led by Jasmine Jasinski and Xin Jia, went back through Voyager 2's own solar wind measurements from the days leading up to its Uranus flyby, they found a steady, unmistakable rise in solar wind pressure in the hours before the spacecraft arrived, a detail that had simply never been cross-referenced against the magnetosphere data in quite this way before, sitting in a completely different part of the archived dataset from the readings scientists had spent decades poring over. Something out there in space had been compressing the solar wind into a denser, more forceful stream just before Voyager 2 made its closest approach. Modeling what that kind of compression would actually do to a planet's magnetic field using simulation techniques and computing power that simply didn't exist in any accessible form back in 1986 produced an almost exact match for the strange, lopsided environment Voyager 2 had recorded decades earlier. The rare solar wind event had squashed Uranus's entire magnetosphere like a fist closing around a balloon, compressing the energetic electrons into a thickened, intensified radiation belt while squeezing nearly everything else out entirely, the way pressure squeezes juice out of a piece of fruit. According to the researchers' own modeling, that kind of extreme compression only happens to Uranus's magnetic field around 4% of the time. Voyager 2 had exactly one flyby, one brief window lasting only a matter of hours, to ever study this planet up close, and by pure chance, it happened to arrive squarely inside that rare 4% window. Run the numbers the other way, and the strangeness gets even sharper. Across the entire multi-year approach to Uranus, across every possible law. The day the spacecraft could have made its closest pass, the mission's one and only shot at this planet landed on one of the roughly 1 in 25 windows where the data it collected would end up systematically misleading an entire scientific field for decades. Nobody planned that, and nobody could have. Trajectory planning for a flyby happens years in advance, locked in by orbital mechanics and fuel constraints, long before anyone could know what the solar wind would actually be doing on this specific day of arrival, calculations finalized based purely on gravity and geometry, with no way to factor in space weather that hadn't happened yet and wouldn't happen for years. One of the study's lead authors put it about as plainly as a scientist ever put something on the record. If Voyager 2 had arrived just a few days earlier, before that solar wind jet hit, it would have observed a completely different magnetosphere at Uranus, and an entirely different picture of the planet would have made it into every textbook written. Since one considerably closer to the more ordinary Jupiter and Saturn-like environment, researchers now believe the planet usually maintains. Once researchers rebuilt what Uranus's magnetic field actually looks like under normal uncompressed conditions, the picture of its moons changed along with it. Scientists had long assumed that Titania and Oberon regularly drift in and out of Uranus's magnetic field as they orbit, spending significant stretches of time completely outside its influence, based on the compressed, artificially shrunken field Voyager 2 happened to observe. The corrected model shows that assumption was itself an artifact of that same temporary squeeze. Under normal conditions, researchers now believe those two moons actually spend the overwhelming majority of their orbits sitting fully inside Uranus's magnetic field, constantly exposed to its variations rather than only occasionally brushing against it, orbiting well within a magnetic bubble that, under typical conditions, extends considerably farther out than the compressed version Voyager 2 happened to measure. That distinction matters enormously because it's exactly the kind of sustained magnetic exposure that would make the Europa-style ocean detection method actually work, if there's a hidden, electrically conductive ocean down there to find. The reason scientists found no evidence of oceans on Titania and Oberon wasn't necessarily because there aren't any. It may simply be that Voyager 2 studied those moons under the one specific set of conditions where the ocean detecting technique itself couldn't have worked properly, even if an ocean was sitting right there beneath the ice the entire time, hidden not by any flaw in the detection method itself, but by the sheer bad luck of measuring it during the one window when the underlying physics briefly stopped cooperating. Sit with that for a second, because it's a genuinely strange kind of discovery. Nobody launched a new mission to make it. No spacecraft got any closer to Uranus than it already had, decades earlier. The entire finding came from realizing that a single 40-year-old observation had captured an edge case, a rare and temporary weather event in space, and had been quietly mistaken for the norm ever since. It's the scientific equivalent of judging an entire ocean's character from one freak once in a while. Generation storm, simply because that storm happened to be the only time anyone ever looked. That correction doesn't prove Titania and Oberon have oceans, and it's important to be precise about exactly what changed and what didn't. What changed is the confidence with which scientists could previously rule oceans out. The absence of a detected signal in 1986 is no longer meaningful evidence against an ocean, because the conditions during that flyby were never capable of revealing one in the first place, even hypothetically. The moons have gone from a settled no back to a genuinely open question, one that current models suggest is now worth serious consideration rather than one that was already closed. Confirming an answer either way will likely require a dedicated future mission, something planetary scientists have already recommended as a priority in recent surveys of where the field should focus next. A proposed Uranus orbiter and probe, a spacecraft that would spend years actually orbiting the planet and its moons rather than passing through in a matter of hours, doing exactly the kind of sustained magnetic monitoring that a single 1986 flyby was never built to provide, gathering the kind of long, continuous baseline of measurements that could finally distinguish a genuinely calm, empty moon from one quietly hiding a global ocean beneath a shell of ice. There's a broader lesson embedded in this story that reaches well beyond Uranus itself, and it's worth sitting with before moving on. Voyager 2's Uranus flyby wasn't a poorly executed piece of science. Every instrument worked exactly as designed, every measurement was recorded accurately, and the scientists analyzing that data in 1986 drew entirely reasonable conclusions from what they had in front of them, using the best tools and the best understanding available at the time. The problem wasn't the data, it was the complete absence of any second data point to check it against. A single 6-hour snapshot mistaken for a permanent, representative picture simply because it was the only picture anyone had, with no follow-up mission ever launched to confirm whether that first impression held up over time. That's a risk baked into any single flyby mission, and it's part of why planetary scientists have increasingly pushed for longer orbital missions over brief one-time flybys whenever budgets and trajectories allow. Precisely because a single pass, however carefully executed, can never fully distinguish between what a planet is usually like and what it merely happened to be doing on one particular afternoon. A distinction that, in Uranus's case, took nearly 4 decades and a small revolution in computational physics to finally untangle. It's also worth appreciating what this discovery says about the enduring value of data that seems, on the surface, to have already told its story decades ago. When Voyager 2 sent back its Uranus measurements in January of 1986, computing power sufficient to model space plasma physics in the kind of detail Jasinski and JWST team eventually used simply didn't exist in any practical, accessible form, confined largely to specialized research supercomputers, running calculations that would take an ordinary laptop today only seconds to complete. The tools needed to notice the solar wind compression, to model its effect on the magnetosphere, and to connect that effect back to the mystery of Uranus's moons had to be developed across nearly 40 years of subsequent advances in computational physics before anyone could actually go back and ask the right question of data that had been sitting in an archive the entire time, patiently waiting through the rise of the internet, the smartphone, and modern machine learning before the specific analytical tools finally caught up to what the data itself had been quietly recording all along. The measurements were complete in 1986. The ability to fully understand what they meant took decades longer to catch up. So here's where that leaves things right now. Voyager 2's Uranus flyby, once treated as one of the mission's stranger, harder to explain results, has been recast entirely, not as evidence of a permanently bizarre planet, but as a single unlucky snapshot of an otherwise fairly ordinary magnetosphere caught during a rare 4% window of extreme compression. 2 of Uranus's icy moons, written off for decades as unremarkable balls of ice with no hidden oceans, are now back on the list of genuinely plausible candidates for subsurface water, reopened by nothing more than a careful second look at data that had been sitting untouched since the Reagan administration. Think about what that actually says about how much more might still be hiding unnoticed in decades of other archived spacecraft data scattered across NASA's and other agencies' data repositories, gathered by missions long since concluded, analyzed once with the tools available at the time, and then largely left alone. Voyager 2 alone carried instruments studying Jupiter, Saturn, Uranus, and Neptune, each encounter generating its own trove of measurements that were, by necessity, interpreted using whatever modeling capability existed at that specific moment in the 1970s and 1980s. If a single, celebrated Uranus flyby could sit for 38 years before anyone connected its own solar wind readings to its own magnetosphere data in quite the right way, it raises a genuine, open question about how many other quietly misleading snapshots might still be sitting in plain sight across the rest of that same archive, waiting for the right combination of curiosity, computing power, and a researcher willing to ask an old data set a new question. No new spacecraft, no new mission, no new observation, just better tools, better models, and researchers willing to ask whether a 40-year-old answer might have been shaped more by timing than by truth. Whatever a future orbiter eventually finds when it finally gets there, the story of how that question got reopened in the first place is itself a reminder that some of the most significant discoveries left to make about our own solar system may not require a single new mission at all, just someone willing to look again at what's already been sitting quietly in an archive, waiting for the right question to finally come along.